Welcome to Ask and Learn.
All right, we start by drawing free body diagrams for this situation. So define the coordinate system such that downhill is positive x, and upwards is in the direction of the normal force, that's positive y. Okay, so when the cyclist is going down, the force of gravity acts at an angle theta, obviously, and there's a normal force acting upwards, obviously, but the force of friction is acting uphill. It's opposing the motion, right? So when the cyclist is going uphill, this time gravity alone can't move the cyclist. So there's gravity, force, normal force, and applied force, Fp. This is the force that will give us the power that we need at the end of this problem. So this is acting uphill, and force of friction opposing this motion is acting downhill. And so let's just simply resolve forces, apply Newton's second law in the x direction in both cases. So for downhill motion, you have the mg, the horizontal component of force of gravity, mg sine theta, minus the force of friction, FFR, is equal to 0, no net acceleration. Therefore, because it's going at constant speed, therefore the force of friction is mg sine theta. Here you have Fp minus the applied force minus force of friction minus mg sine theta. Or I should say negative Fp plus FFR plus mg sine theta equals 0. Therefore, applied force is force of friction plus mg sine theta. And assuming this is the same friction force acting on the bicycle cyclist system, we just replace the force of friction from here. So you have mg sine theta plus mg sine theta giving us 2 mg sine theta. Okay, and then all we have to do is use the formula for power. Power equals force times velocity. It's the constant speed the cyclist is traveling at. So this is 2 mg sine theta times v. And so plugging in values, we have 75 kilograms for mass times 9.8 meters per second squared for g times sine 6 degrees times velocity, which is 4 meters per second, giving us 610 watts of power. And that's it.